is the last session of the boot camp, and Nima's going to give us some exercises.
So I'm going to go until 3:30, and then we'll have another break. Like I said, the main thing I wanna prove now is that if you have a matroid, then its polynomial is going to satisfy this complete log-concavity, whose definition I gave you. So it turns out that the first time that we encountered this and we empirically observed it, we looked around for tools to basically use to prove it. Turns out there is this beautiful theory, Hodge theory, which I mentioned in the beginning of the talk, and you can use that theory to prove this statement. But today I want to give you a different proof. Okay. So, but before going to this different proof, let me say that now we have found that this definition is equivalent to a lot of other definitions that different groups have found out. So a strong log-concavity is the thing that Gurwitz used to derive inequalities on the coefficients of polynomials. So strong log-concavity, like I said, is the simpler thing where you replace directional derivatives by partial derivatives. So now we know that these two are basically equivalent, at least for homogeneous polynomials. So whenever you have a shadow of a Hodge theory, there are inequalities in Hodge theory, which I might get to, which give you a polynomial. So as long as you have these so-called Hodge-Riemann inequalities in some algebra, you magically get a polynomial which turns out to be log-concave. And from any polynomial that's log-concave, you can also construct an algebra where you have these inequalities. I might get to this if I have time. It also turns out to be equivalent to a notion of high-dimensional expansion. Won't get to that in this talk, but we'll see that later on in the semester. And there is also an independent notion developed by Peter and Juni Ha. And I'll mention what this notion is, but it's basically equivalent to complete log-concavity. Okay? Complete log-concavity, I've written again the definition here. You start from a polynomial, you take directional derivatives along positive directions, and you want the end result to be log-concave, right? So as I mentioned, derivatives along all possible directions is not really necessary. You can only take directions along the standard basis, and as long as the end result is log-concave, you have this entire complete log-concavity. So this is a statement that we showed, that if you have a polynomial, as long as it satisfies some non-degeneracy assumptions, which I'll mention, it's enough to only check this property when the number of derivatives you're taking is the degree of your polynomial minus 2. So the end result is a degree 2 polynomial. And as long as the directions are along the standard basis, so you're taking real partial derivatives. Okay.
But you need the connectivity.
You need the connectivity.
Actually,
yes.
The funny thing is that one of the reasons I needed that thing was to fight with the connected components.
You needed what?
Because I had the situation, the problem which I was interested was to check whether polynomial can be factorized into product of two polynomials.
Yeah, exactly. That's to prevent that.
Over there you get this problem, and you need that possibility.
Yeah, you need something like this. I'll mention what it is. Yeah, exactly. And then, okay, so once you get, so this is just for simplicity over d-homogeneous polynomials. You can reduce everything to d-homogeneity. So once you get to a degree 2 polynomial, the thing that you have to check for log-concavity is that the Hessian of the degree 2 polynomial, this is like a constant matrix, right? Doesn't matter which point you evaluate that. This thing has at most one positive eigenvalue. So this notion that Peter and Juni Ha developed is basically the premise of these two theorems. Okay? So you call a polynomial belonging to this class if it satisfies the premise of these two theorems. And of course, now the hard thing becomes proving that certain operations preserve this property. You have a question?
The second one was no.
Yeah. The second one is easy. Yeah. Second one is very easy. Okay. So let me give you 2 examples of this. So we are going to see what this means for bivariate homogeneous polynomials and for Matroid polynomials. Okay. So if you have a bivariate homogeneous polynomial, you can always, it's associated to basically a sequence, because if you have g of z1 and z2, or let me, g of x and y, it's always of this form, a0 x to the d, y to the 0, plus a1 x to the d minus 1, y to the 1, up to ad x to the 0, y to the d. Okay. So once you take a bunch of partial derivatives of such a thing until you get to a degree 2 polynomial, that degree 2 polynomial is going to have 3 consecutive terms of this. Okay. And its Hessian is going to be of this form. So the Hessian of basically partial x to the k, partial y to the d minus k minus 2. I might be, so of g. This is going to end up being a 2 by 2 matrix, which is of this form. So you get a to the a of, maybe, let's switch this up, minus k and y to the k minus 2. Okay. So you get a of k minus 2 divided by d choose k minus 2, a of k divided by d choose k, a of k minus 1 divided by d choose k minus 1, and a of k minus 1 divided by d choose k minus 1. And the whole thing multiplied by d factorial. Okay. So in the binomial coefficients that you see, there are basically 2 kinds of factorials. There is a d factorial, which basically cancels out with this global d factorial. The other factorials coming from taking derivatives of x and y. Okay. So you end up getting to this sort of a polynomial, right? To this sort of a matrix. Now, this matrix has positive entries, right? So its trace is positive. So it's going to have either 2 positive eigenvalues or 1 positive eigenvalue, 1 negative eigenvalue. And the way you can determine which is the case is by computing the sign of the determinant. Okay? So having at most one positive eigenvalue is basically equivalent to the determinant of this being negative, which means that ak divided, or ak minus 2 divided by d choose k minus 2 times ak divided by d choose k is less than ak minus 1 divided by d choose k minus 1, the whole thing squared, right? So we've already seen this property. This is exactly the same as the Newton inequalities, right? Or ultra log concavity, okay? So now let me mention what this being connected support means, okay? This is a good place to illustrate it. So if you have a sequence which satisfies these local conditions, right? It's not, so when people are talking about log-concave sequences, what they usually mean is log-concave sequences with no internal zeros, okay? So if you have, let's say, two sequences which are log-concave or ultra log-concave, let's say this one goes up to ak and the other one starts from like, so if you have a sequence of this form, which has internal zeros, okay? So it can still satisfy inequalities of this form, But you're not generally considering this log-concave because really it's composed of two separate log-concave sequences. One is the first one before the first zero, and the other one is the one after the second zero. Okay? What's happening is that inequalities of this form become sort of degenerate at these points. Okay? So being connected support is exactly to prevent things of this form. Okay? So if you have a sequence where the local constraints are satisfied, and you form the corresponding bivariate generating polynomial, it's not going to be log-concave. It's not going to be completely log-concave if it has internal zeros. Okay? So being connected support is a condition that prevents things of this form. And for multivariate polynomials, what that means is, so we call G mu connected support. If whenever you take a bunch of partial derivatives, so partial derivative along EI1, EI2, up to EIK,
This sequence cannot satisfy Newton inequalities.
Why not?
Because it's supposed to be concave, not necessarily. If it's concave by neighbors, it's concave as like.
No. I mean, so let's say you have this sequence, right? So you have 1, 0, 0, 0, 1, right?
So this one.
So which one of the inequalities is?
One is not concave because 0 is supposed to be greater or equal. Any guy in the middle is supposed to be greater.
Right. Where is that inequality failing in this sequence?
You're saying it's not a local condition, right?
No, but I think you can combine local condition to prove.
So zeros are the thing. So when you're basically combining the local conditions to get the global conditions that you're talking about, when you have zeros, you're dividing by zeros and things get messed up. So you can just check that for this sequence, you have inequalities of this form always, right? But it's not connected support. Okay?
So you need two zeros. So you need two consecutive zeros, and then it's fine.
Yes. I've put 2 consecutive zeros here too. So the condition that you really need is this, that when you take partial derivatives of your function, this time I'm not going to take partial derivatives until I get to a degree 2 polynomial. I stop this somewhere before I get to a degree 2 polynomial. Then the polynomial cannot be decomposed into a sum of basically h1 and h2, where h1 is on a set of variables, h2 is on the complement of that set. Right? So h1 is on R of basically the i's, I in S, and h2 is in R of the i's, I not in S. Okay? So you want this to never happen. Okay? So why does that prevent internal zeros from happening in this case? If you have internal zeros, by taking derivatives, you can basically zoom in on this window, right? The last guy which is non-zero here, the first guy which is non-zero here, and you can just kill off the other terms, right? Now this thing is going to be something of this form, ak x to some power, but y to the 0, plus ak plus 3, there might be some coefficients here too, some factorials here too. X to the 0, y to some other power, right? This is written already as a sum of 2 polynomials, one on x, one on y, right? So having that condition prevents internal zeros from happening in the bivariate case, and that's the sort of thing that you need in the general case too. Exactly that condition that I've written earlier. All right. So now, before we again go to the break, let me just do the Matroid case and finally prove that Matroid satisfy the promise of this, or the premise of these theorems. So the cool thing that happens for Matroids is that Matroid polynomials are closed under taking partial derivatives. Okay? So if you start from some Matroid m and you look at g of m, when you take the partial derivative with respect to, let's say, zi, this is the same as the Matroid polynomial for m contracted with I. Is this the sign of contraction? No? Okay, sorry. I always confuse the two. Okay? So when you take the partial derivative with respect to zi, you're basically throwing away all bases that don't contain zi. And then from the bases that contain zi, you're just throwing out I. Right? So Matroid polynomials are closed under the operation of taking partial derivatives. And then you can also check that they can never be decomposed. So they also satisfy this connected support condition. So all it boils down.
Almost from the exchange property, or?
Basically, if you connect bases of Matroids, if you connect basically bases of Matroids by connect bases of Matroids that connect two bases whenever they differ in only two elements, this graph becomes connected. This is falls from that. So all it boils down to is to prove the right-hand side for Matroids, but on the right-hand side, you're talking only about degree 2 polynomials, right? So the Matroid must be a rank 2 Matroid. Okay. So rank 2 Matroids, we know them all, and we know exactly what they look like. So here is a picture of a rank 2 Matroid. So let's say that the Matroid is on elements 1 to up to n. Because I'm of rank 2, I can represent bases using edges between the nodes, right? Whenever there is a base containing two elements, I just connect them. So you can basically verify that using the Matroid axioms, the graph that you're going to get here is a complete multipartite graph. So there is a way to partition the elements into sets so that whenever you pick two vertices from different sets, you have an edge. And whenever you pick two vertices from the same set, you don't have an edge between them. These are exactly all Matroids of rank 2. So then for a Matroid of rank 2, now you can exactly write down the polynomial, the corresponding polynomial. And it's going to be of this form. It's going to be 1/2 z1 up to zn times a matrix, which is basically the adjacency matrix of that graph. So zeros on blocks on the diagonal and ones everywhere else, times z1 up to zn. Okay, you can just see that this is exactly the generating polynomial of the Matroid. So I have to verify that the Hessian of this thing has at most one positive eigenvalue, but of course the Hessian, I've already written it down for you. It's exactly this matrix. So why does this matrix have at most one positive eigenvalue? So you can just observe that this matrix is basically the all ones matrix minus something which has ones on the blocks on the diagonal and zeros everywhere else. Right? So the polynomial or the matrix that you start with is a rank 1 matrix, and then you subtract something which is PSD from it. So when you start with this matrix, you have one positive eigenvalue, and this can only take the eigenvalues down. Okay? So in the end, you're going to end up with something which has at most one positive eigenvalue. All right, so I think we should take a break.
So by the way, it's a simple stuff, but it was in my paper with Friedland. Just observation. Even
That for matroids? Oh, okay. I didn't know.
it's a simple, of course. It's very simple. So actually, they're not. If those blocks, if those parts have the same cardinality, there is a very simple proof based on tensor product. So if they have the same cardinality,
You get J minus I tensor something?
yes,
Okay.
and you immediately get what it is.
Yeah, you should show me this. So I think we should take a break, right? Yeah. And afterwards, we're going to look at the exercises, some of them.
Yeah. Again,
How long
say
is the
it's-
break? Long time ago.
Yeah, so 20 minutes, right? Or I don't know. When was the original, when was it originally supposed to start?
3:15. Yeah, 3:15.